Hello everybody, and welcome back to Math 410 Abstract Algebra. So, before I get into this video, I just want to have a little bit of a chat with you. And I want to let you know that I'm not planning on having the rest of the semester be like this, where I'm just pre-recording lectures and posting them on YouTube. I'm kind of trying right now to go through a plan where we have just classes via Zoom and people can come in. I can split you all up into separate kind of like little chat rooms on Zoom so you can talk about problems, and hopefully the idea is by Monday we'll be able to have class in a regular way. I just need some time to plan that out a bit. And so, well, today's going to be a pre-recorded lecture. I'm hoping today's the only day where that needs to happen. And are we going to be online for the rest of the semester? I'm not sure. I wouldn't be surprised if so, because I definitely don't want to go back for the next few classes to in-person, just given how many COVID cases are at the college right now, and how terrifying I find that to be. So, we online probably at least for the next week, and then I'm probably going to keep going online after Thanksgiving because, oh my gosh, people going home, spending time with family, probably in close contact after Thanksgiving. I don't think we should be coming back in person, but who am I to disagree with the college? I don't even have any. So, until Dr. I said any of that. So, yeah. So, plan is just for today to be pre-recorded. It's just kind of to get us through today's class, Friday's class. I'm actually recording this on Thursday. To get us through class today, and next week I will hopefully be doing something a bit more interactive with you all. So, plan for today. We are going to continue into our Rings 2 packet and talk about several different things that we had kind of looked at back in group theory, like homomorphisms, isomorphisms, first isomorphism theorem, etc., and try and generalize them to looking at things from ring theory instead of just group theory. My next office hours are going to be Monday at 10 o'clock and from 2 to 3. As we move online, I don't plan on office hours being any different. Those will still be at the same times and will still be online. Don't forget, why did I say Tuesday? I'm sorry, I'm completely out of this. Exam 2 is going to be due next Wednesday at the end of the day. Any questions or comments before we get started? Haha, we're on YouTube, so, and I'm in an empty room talking to myself. So, did you know that my old car is like e to the x? How so? Well, you can derive it all you want, but you're never going to get anywhere. Okay, so last time we had started to talk about quotient rings. We looked at what an ideal is. We said that S is an ideal of R, means that S is a subring of R, with the extra property that such that for all S in little s in big S, and the little r in big R, S times R and R times S are both going to be elements in S. So if you take anything in the ideal and you multiply by anything in the ring as a whole, you're always going to get back something in the ideal. Not something that's necessarily true for an arbitrary subring, but will be true for ideals. And what we said is that if R is a ring, and S is an ideal of the ring R, then we can form a quotient ring, R mod S, by taking the set of all of the cosets of S and R. Remember, the cosets are just the summings of the form little r plus big S, where little r can be any element from the ring R. And we said that that's going to form a quotient ring under the ring operations. You add two cosets, little r plus S, little t plus S, by just adding together the coset representatives, little r plus little t plus S. And we can multiply two cosets by taking little r plus S times little t plus S, and that's just going to be defined to be little r times little t plus S. And last class we looked at some examples of ideals and behavior of things in the quotient ring. But we didn't answer the question last time of why was it necessary for S to be an ideal of the ring R? in order for this to give us a ring structure. Why couldn't we just have a quotient ring where R is a ring and S is just an arbitrary subring of R? So I thought what we would do today is we would start by exploring that. Why is it necessary for S to be an ideal of R? And to do that, we're going to look at how things go horribly wrong when we look at an example of what happens if we try and make a quotient ring where we have a ring R and a subring S that doesn't form an ideal. And so the thing I want to look at is going to be the one from the front page where our ring is going to be the ring of all continuous functions over the real numbers. And our subring S, go back in my notes, our subring S is just going to be the ring of all differentiable functions over the reals. And so here, something to note, as we discussed in Wednesday's class, S is a subring of R, because if you have something that's differentiable over all the reals, it automatically has to be continuous. Something, hopefully, still on Calc 1 maybe a little bit, and if not, get ready for real analysis. S is a subring of R, but not an ideal of the ring R. Is this recording? It is. Because, for instance, you can multiply things in S by things in R, like, for instance, the absolute value of X times the constant function 1, which is something in R times something in S. But when you multiply them, you'll get back the absolute value function, which is not an element in S anymore. So I claim things are going to go horribly wrong if we try and make a quotient ring here on R mod S. Let's see why that is. So as an example, I want to take, where are my notes? Okay, I want to take three different functions that are in R. I'm going to take the function f of x, once again, is the absolute value of x. So that's going to be an element in R, not an element in S. I'm going to take the function g of x, is the constant function 1. The g of x is just always equal to 1, no matter what you plug in for x. And h of x is going to be the constant function 0. H of x is just 0 no matter what you plug in for h. Or both of these are going to be elements in S specifically. And I want to take a look at what happens when we look at the cosets f of x, g of x, and h of x plus s. Let's see what happens. So if we were to take g of x plus s, if we were to try and look at the coset of s corresponding to g of x in our set of cosets, in our supposed quotient ring, well, that would be the constant function 1 plus s, which I claim is going to be equal to s. So why is g of x plus s going to give us back the same thing as s? Well, that's just going to be because g of x is already an element in S to begin with. And similarly, h of x plus s, the 0 function plus s, will just give us back the set S, since h of x is also going to be an element in S. So in other words, g of x plus s and h of x plus s are both just going to give us back the set S again. If we were to take everything in S, add g of x to it, we'll still just get back S. Ditto with h of x. And this is kind of using properties we saw back when we were doing group theory. So now, I want to try looking at this thing and see what happens if we were to take f of x plus s and multiply that by g of x plus s. Let's say h of x first. If we were to try and do f of x plus s times h of x plus s, which if we had a nice quotient ring structure, we should be able to do, well, this product is defined to be, by definition, f of x times h of x all plus s, which, if we set that up, is going to be equal to the absolute value of x multiplied by the 0 function plus s. No matter what you plug in for x, absolute value of x times 0 is just going to be 0. So f of x plus s times h of x plus s is in fact just going to give us back s. Makes sense, right? You multiplying something by 0 plus s, going to give you back s. What if I told you that is wrong? Because check this out. Uh-oh. Didn't get my eraser. What if I told you that what we just showed doesn't actually work that way? Because we can also say, well, another way we could take f of x times f of x plus s times h of x plus s is, since h of x plus s is equal to g of x plus s, because they're both just going to give us the set s again, this should also be equal to f of x plus s times g of x plus s. Since g of x plus s and h of x plus s are giving us back the same quotient. But this time when we multiply it out, we would get f of x multiplied by g of x all plus s, which is the absolute value of x times 1 plus s, which is the absolute value of x plus s, which is very much not equal to s. Since f of x plus, or since the absolute value function f of x is not an element in s itself. And here's the rub. We've just shown that this expression, f of x plus s times h of x plus s, is both equal to s and at the same time is not equal to s. Or is not an element. What did I say? Not equal to s, sorry. Not an element of its first single element. So the same product of two cosets is both giving us s and not s at the same time. What's up with that? Well, the issue is that if f of x, or if s is not an ideal, the multiplication operation is not going to be well defined. In a similar way to what we saw in group theory, where if h was not a normal subgroup of G, then G mod h didn't give us a well-defined binary operation structure. Same is going to be true here. Multiplication is going to behave in very wonky ways in which things are equal to s and not s at the same time, which is no bueno. So, moral of the story is, if s isn't an ideal of R, then R mod S is not a ring, since multiplication is not well defined. If you represent the same coset in multiple ways, the products can come out differently each time. So that's why we didn't formally prove that everything works out nicely if S is an ideal of R, but trust me, it works out. I don't feel like proving that because that's kind of another long argument, and it's pretty similar to the argument for why if H is a normal subgroup of G, then G mod H forms a well-defined quotient group. Same basic thing, just replace the word group with rings. But if S is not an ideal, just like if H was not a normal subgroup of G, then the operations we would want to behave nicely do not behave nicely. Okay, so next up, I'm going to talk a little bit about ring homomorphisms and ring isomorphisms. Which is pretty similar to what they were for group homomorphisms. We just have to account for what happens now that we have an extra operation. And it's going to turn out that a ring homomorphism phi from a ring R to a ring S is a map so that for all elements little a and little b in R, we want it to be the case that phi of a plus b is equal to phi of a plus phi of b, and we want it to be the case that phi of a times b is going to be equal to phi of a times phi of b. So in other words, a ring homomorphism is just like a group homomorphism, except it behaves nicely with respect to both addition and multiplication. That if you add two things and then apply the map phi, you get the same thing as if you took phi of each individual thing to start and then added them together. And similarly, if we had two elements A and B, if we multiplied them and then applied phi, we want to get the same thing as if we take phi of each one and then multiply. Where one thing to note is that over here, our multiplication is using the multiplication operation in R, whereas over here, we're using the multiplication operation in S. So if R and S are different rings and they don't have the same operations, multiplication, here, what we call multiplication could mean different things. Here, A and B are elements in R, so this should be multiplication using the operation from R. Here, phi of A and phi of B are going to be elements in S, so if we multiply those two things, it's using the multiplication operation in S. And ditto for addition. Here, addition is being done in R. Here, addition is being done in the ring S. So, before I do an example, I want to take a quick look at talk about what a ring isomorphism is. And just like how a group isomorphism is a group homomorphism that's one-to-one and onto, a ring isomorphism is a ring homomorphism that is one-to-one and onto. And just like how if we have two, what am I calling? We said that two groups are mathematically the same if there's a group isomorphism between them. Same can be said to be true about two different rings. That if you have two rings and there's a ring isomorphism between them, then those rings are mathematically might as well be the same thing. They behave in exactly the same way. So let's take a look at a ring isomorphism, trying to put it into practice. Just so we can kind of see what's going on. Basically, if you're trying to show something's a ring isomorphism, it's exactly the same as showing that it's a group isomorphism. You just have one extra step to check, and that's that you have to show your map behaves nicely with respect to two operations instead of just one. So the example I want to look at is going to be the map phi from the complex numbers to the complex numbers, where we're going to define phi of z to be the complex conjugate of z. Dr. Gerstel, I haven't had complex analysis. What does it mean to put a bar over the z? What that really means is to take a complex number, a plus bi, and map it to a minus bi. So if we're looking at points in the complex plane, let's say a plus bi is going to be here, phi of a plus bi would be the same point reflected over the real axis, or the x-axis, if you will. So phi of a plus bi would be something like here. Basically, our map phi is taking points in the complex plane and reflecting them over this horizontal axis. So anything above the real axis gets mapped below it, anything below it gets mapped above it. So this would actually be phi of a minus bi. And I claim this is going to give us a ring isomorphism. So let's see if we can prove that. Oh, let's see. All right, Megan, which would you like to prove first? We have 4 things we need to show. We need to show that, technically 3, we need to show phi is a ring homomorphism, which involves proving 2 separate things. We need to show that phi is 1-to-1, and we need to show that phi is onto. Megan, which would you like to prove first? I'm going to just propose that we prove phi is onto first. That's ridiculous, Megan. We're going to start by proving phi is a ring homomorphism. Though, to be clear, for the record, you could prove these things in any order, just like you could with group isomorphisms. So, our goal, so we're going to prove that phi is a ring isomorphism. And we're going to start by showing that phi is a ring homomorphism. And to do that, we need to show these 2 things. Given any 2 complex numbers, if we add and then apply phi, we get the same thing as if we applied phi to each one and then added. We also need to show that if we multiplied our 2 complex numbers and then applied phi, we would get the same thing as if we applied phi to each one and then multiplied them together. Let's give that a go. So given any, I'll call it a plus bi and c plus di in the complex numbers, if we were to take phi of a plus bi plus c plus di, meaning if we were to add and then apply phi, well, that would give us, let's see, a plus bi plus c plus di would be the same as taking a plus c plus b plus d times I. And what would we get if we tried to plug in a plus c plus b plus d times I into this function? Well, this function leaves the real part of the input alone, so the a plus c is going to stay the same, but it's going to take the negative of the imaginary component. In other words, the piece that we're multiplying by I. Positive b becomes a negative b, so positive b plus d times I is going to become negative b plus d times I. So that's what phi of the sum would be. But we can redistribute and say, I could rewrite this as a minus bi plus c minus di, because we get a positive a minus b times I, a positive c, and a minus d times I. Remember, this minus sign gets distributed to the b and the d. So we end up with a minus bi plus c minus di, which is the same as taking phi of a plus bi plus phi of c plus di. So phi does behave like a homomorphism with respect to addition, and that if we added our 2 complex numbers, and then applied the map phi, we got the same thing as if we took phi of each complex number individually and then added them together. So we're still not done. We still need to show, what's that, Megan? You want to show 1-to-1? Get out of here. So we still need to show, in order to be able to prove that phi is a ring homomorphism, we still need to show that the same property behaves nice with respect to multiplication as well. That if we multiply and then apply phi, we get the same thing as if we applied phi to each piece and then multiply together. So let's try that out. So we proved the addition part. If we were to take phi of a plus bi times c plus di, well, that's going to give us what? AC minus BD plus BC plus AD times I, phi of all that technically. Why is that? Well, multiply out. We would FOIL. We get an AC plus BCI plus AD times I, and a plus BD times I squared, which, using the fact that I squared is -1, BD times I squared just gives us a negative BD, hence this term here. All right, neato burrito. So when we plug all this into phi, the real part is going to stay the same. So we'll still have an AC minus BD. The imaginary part, though, becomes a negative, so we end up with minus BC plus AD times I. And then we can unravel and factor this expression to be of the form A minus BI times C minus DI. Why? Because if we multiply this out, we get an AC minus BI times minus DI becomes plus BDI squared, which is a minus BD. We get a minus BCI, we get a minus ADI, and so everything in here is equal to what line above it. And then A minus BI times C minus DI will in fact just be phi of A plus BI times phi of C plus DI. So now we've shown that phi is a ring homomorphism because it behaves nicely both with respect to addition and with respect to multiplication. So now we have that our phi is a ring homomorphism. We still need to show that it's one-to-one and onto in order to show that it's a ring isomorphism. Megan, you want to do one-to-one next? Finally, she's agreeing with me. So to show that phi is one-to-one, what we're going to do is we need to assume that phi of A plus BI is equal to phi of C plus DI, and then show A plus BI has to be equal to C plus DI. In other words, show that if you plug in the same thing, or if you plug in two things into the function and get the same output, the inputs have to be the same. Well, we can do that by saying if phi of A plus BI equals phi of C plus DI, when A minus BI is equal to C minus DI, well, from there you can say A has to be equal to C, and B has to be equal to D, which in turn tells us that A plus BI is equal to C plus DI. So phi is one-to-one because if you take phi of thing 1 equal to phi of thing 2, you can show that thing 1 has to be equal to thing 2. And the last thing we need to check is that phi is onto. Well, this one's not so hard. To show phi is onto, we need to show given any element in our codomain, the complex numbers, there's something in the domain, which is also the complex numbers, that maps to it. Well, we can do that by saying given any element A plus BI in the complex numbers, A plus BI has to be equal to phi of some other complex number. Which complex number, you might ask? Why, A minus BI, of course. Because phi of A minus BI will give you A minus negative BI, which is the same as A plus BI. So our map phi is a ring homomorphism, meaning it behaves nice with respect to addition and multiplication. It's one-to-one, it's onto, and therefore phi is a ring isomorphism. So that's kind of the basis of how ring isomorphisms work. It's the same as group isomorphisms, really. You just have to do one extra step, which is check two operations that it behaves nicely with, and not just a single one. And so now, I want to talk about a few theorems related to properties of homomorphisms and isomorphisms. So here's the first theorem. That's that if you have that ring 1 plus 1 times 1. I don't know why I wrote it this way instead of just saying R. Whatever. If you have 2 rings that are isomorphic as rings, then R1 under addition and R2 under addition must be isomorphic as groups. So if you have 2 rings that happen to be isomorphic as rings, then with respect to the addition in the 2 different rings, you'll get that they'll also be isomorphic as groups under addition. And I'm not really going to prove that. I could, but proof's pretty short. Basic idea is that if they're isomorphic as rings, then you have a ring homomorphism from one to the other. And if you happen to have a ring homomorphism from one ring to the other ring, or a ring isomorphism, I should say, it's also going to be a group isomorphism under addition. The reason is, part of being a ring homomorphism is that you need to be a group homomorphism with respect to addition. That's part of it. The other part's multiplication. But if you have the ring homomorphism, you have a group homomorphism. If your ring homomorphism is 1-to-1 and onto, well, it's still going to be 1-to-1 and onto as a group homomorphism. And so, boom, if you have a ring isomorphism, you have everything you need to have a group isomorphism as well. So isomorphic rings are going to be isomorphic as groups as well. However, you might be wondering, Dr. Gerstle, is the reverse true? If 2 things are isomorphic as groups, will they have to be isomorphic as rings as well? It's a good question. I'm proud of myself. Pat myself on the back for coming up with it. Turns out the answer is no. It's possible to have 2 rings that are isomorphic as abelian groups, or groups under addition, but not isomorphic as rings. So let's see if we can find an example about this. This doesn't work as a vice versa argument. So I'm going to look at 2 rings. The first ring is just going to be the complex numbers with the usual addition and multiplication of complex numbers. The second ring I want to look at is R2. So the set of all 2-dimensional vectors over the reals, where R2 is going to be defined to be a ring under the operations A comma B plus C comma D is just going to be A plus C comma B plus D. And we're going to define multiplication in a weird way. We're going to say that A comma B times C comma D is just always going to give us 0, 0. If you multiply any 2 things in this ring, you're going to get the 0 element. 0, 0. Dr. Gerstle, that's weird. It is weird. I know it is weird. But here's the thing. This still is going to form a ring. This still gives us an abelian group structure, as you all discussed on actually homework 1 of the semester. This thing forms a group under addition. Its multiplication is closed, because if you multiply any 2 things, you get something back in the ring, namely 0, 0. It's associative, because if you multiply 3 things in any order, you'll always end up at 0, 0. And it has the distributive property, that if you multiply something by the sum of 2 things, you'll get 0, 0, which is the same as taking AB plus AC. You get 0, 0 plus 0, 0, which is 0, 0. So these are both rings. We can say R1 is isomorphic to R2 here as abelian groups. Or, I don't know why I keep saying as groups. As groups under addition, let's say. And you can find a map so you can find a map from R1 to R2 that'll do that by just saying P of A plus BI is just going to be A comma B. We'll let you go through and check that on your own, but it turns out that's that's an isomorphism from complex numbers to R2 with respect to addition. But R1 is not isomorphic to R2 as rings. Actually showing that these two things are not isomorphic as rings, we're not too prepared to talk about yet because we haven't talked about, if you have two isomorphic rings, what properties do they have to have in common? But I'll put it this way. One way you can tell R1 and R2 can't be isomorphic as rings is because the complex numbers do have a multiplicative identity, namely the complex number 1 plus 0i. But R2 does not have a multiplicative identity because if you multiply anything by anything else, it's just always going to get mapped to 0. There's nothing you can multiply a comma b by that'll give you a comma b, assuming a comma b is not 0, 0 to begin with. So if you have two rings that are isomorphic as rings, then they'll have to be isomorphic as groups, as under addition as well. But if they're isomorphic as groups under addition, they do not necessarily have to be isomorphic as rings. They certainly could be, but they don't have to be. So that's it for that first theorem. Another theorem is going to look something as, I hope, something that looks familiar to you. Tells us another way to tell whether or not a subring is an ideal. Bigger piece of talk. And this theorem is going to say that if we let S be a subring of R, then S is an ideal in R if and only if S is equal to the kernel of phi for some ring homomorphism phi from R to some other group or some other ring R prime. So in other words, a subring will actually give us an ideal if and only if that subring is equal to the kernel of a ring homomorphism from R to some other ring. Does that look familiar to you? Well, I hope it looks familiar to you because this is the exact same theorem we had for normal subgroups in group theory. That H is a normal subgroup of G if and only if H is equal to the kernel of some group homomorphism from G to some other group. Same thing here. An ideal, S is an ideal if and only if it's equal to the kernel of phi for some ring homomorphism phi from R to some other ring. Again, the kernel of phi is just the set of all things that are getting mapped to the identity element. Oh, I should probably say which identity element. I hadn't talked about that yet. So for a ring homomorphism phi, we say that the kernel of phi is going to be the set where here phi is a ring homomorphism from R to R prime. The kernel of phi we're going to define to be the set of all elements little r and big R, such that phi of R is equal to the 0 element in R prime. So in other words, the kernel is the set of phi, it's a set of all things in the first ring that are getting mapped to the additive identity in the second ring. Not the multiplicative, but the additive identity. And that's what the kernel of a ring homomorphism is. Same thing that was for a group homomorphism. Now we just have one extra thing we need to keep in mind, which is we're mapping things to the additive identity and not the multiplicative identity of the second ring. We have two different identities we need to check, so we need to distinguish which one we're looking for. All right. Well, if this theorem looked familiar to you from group theory, it was because the normal subgroup version of this theorem was necessary in order to get the first isomorphism theorem. That's right. That's why we care about it here as well, because the first isomorphism theorem works just as well for rings as it does for groups. So if we write this out, This is going to be fit, this time for rings. And it's exactly the same, basically, as the version it is for groups. If you take a ring R and you modify the kernel of a ring homomorphism phi, then that's going to be isomorphic to the image of phi. So we're going to let phi from R to R prime be a ring homomorphism. Not necessarily an isomorphism, but a homomorphism. Then the map phi, or the map psi, I should say, going from R mod the kernel of phi to the image of phi, which you could write as phi of big R, or just M of phi, however you feel like. Then that map defined by psi of little r plus kernel of phi maps to little phi of r is a ring isomorphism. Literally the exact same theorem we saw 2 packets ago in our last group theory packet, the first isomorphism theorem. Exactly the same, you just replace the word group with ring several times. So phi is a ring homomorphism, then the map psi here that we get is a ring isomorphism, as opposed to group homomorphism and group isomorphism, which were the terms we used for the group theory version. But just like with the group theory version of the first isomorphism theorem, this theorem is also going to be useful in showing that a quotient ring is isomorphic to a non-quotient ring. And in particular, if we ever have a quotient ring and a non-quotient ring we want to show are isomorphic, we could just find a homomorphism from R to some other group, to the R to the other ring, where the kernel of phi is the thing we're modding out R by, and the other thing, we want to show that our map phi is a ring homomorphism and is onto. How are we doing on time? 43 minutes almost. Usually I'd stop and answer questions for about 7 minutes or so. Yeah, that's about 1 class's worth of stuff for today. So when we come back on Monday, hopefully we'll do this on Zoom in some semblance of being able to interact with you all, answer questions and such. When we come back on Monday, we will finish this packet off by looking at a couple examples of the first isomorphism theorem for rings, see what questions you had from today's video, and then we will move on to a new packet where we're going to start talking about stuff that's unique to ring theory, rather than this packet, which is basically just how can we take things we did in group theory and generalize to ring theory. The next packet, we'll be doing brand new stuff. We'll start in that about halfway through class on Monday. Hope you all are doing okay. If you're in quarantine, if you've come down with COVID, I want to say I'm here for you. I want to do what I can to help. So let me know, please, if there's anything I can do to help you. Or, as you're watching this, if you have any ideas about how you think would be a good way for me to run class online, because I'm still kind of thinking about that, please let me know. I appreciate any kind of ideas or feedback you all might have. So with that in mind, that's it for me today. Stay, as best you can, stay healthy, stay safe, stay awesome. Like Awesome Possum. Peace out.